Welcome to Pre-Calculus. Today, we will investigate graphs of parent functions, focusing on graphing from a table of coordinate points and analyzing for domain, range, zeros, y-intercept, and horizontal and vertical asymptotes. Let's take a look at two examples to begin. We'll have a total of 4 examples. We'll see 2 here to start. Let's head over to our notes screen. So our first example is the function f of x equals 2 to the power of x. Our first task is to graph the parent function by creating a table of coordinate points. So we'll begin by creating our t-chart. And recall from your work in Algebra 1 and Algebra 2, this left-hand column is going to be our x column. We also call those the domain values. Another name for those numbers is going to be the independent variables. We'll call that right-hand column f of x, which is a way for us to say that those values come from x. We'll use our rule, which in this case, again, is 2 to the power of x. And let's choose for our domain values the traditional 5. See if you can see why we would use these 5. It's -2, -1, 0, 1, and 2. Why do you think that we choose those 5? Because really we could have chosen any x values we like. Well, one reason is that those 5 are centered around 0. They're centered around the origin. So that's a convenient slice of the function's graph for us to catch here as we evaluate and graph. So I'm going to choose another color here, and let's evaluate the outputs or the y or f of x values for each of these x's. So we're going to start with f at -2. And remember, the way that we calculate this is I'm going to take the rule, which is 2 to the power of x, and in any place that I see x, I'm going to substitute that number. So I'm going to substitute -2 here. And at that point, we just want to simplify. We need to remember what happens when I raise a number to a negative power. So it does not make the number negative. In fact, all it does is it flips the number over. It gives us the reciprocal. So 2 to the power of -2 is the same as 1 over 2. See how that flipped over to the power of +2. From there, I can distribute the power of 2 to the 1 in the numerator and the 2 in the denominator. So that's 1 squared over 2 squared. And 1 squared is 1 times 1 or 1. 2 squared is 2 times 2 or 4. And we could convert that to a decimal, 0.25. So that gives us our first coordinate point, -2, 0.25. We'll plot that on the coordinate plane in a moment. Let's finish evaluating these f of x values. Our next number is f at -1. So at this point, we have a feeling about what to do with that -1. This is now 2 to the power of -1. I've just replaced x with that x value of -1. And again, the negative just flips the 2 over to 1 over 2 to the power of +1. And at that point, I can just kind of think about what the power of 1 does to a base. Power of 1 we call the identity element for exponents. So what it does is it just gives us the base back. So half to the power of 1 is simply half. And as a decimal, 0.5. So my second coordinate point over here on the left is -1, 0.5. Our next f of x value is f at 0. That's 2 to the power of 0. So we had to remember what negative exponents did. They flipped the base over. We also need to remember what a 0 exponent does. It's tempting to say that that turns into 0, but it never does. It turns into 1. Anything to the power of 0 equals 1. So that gives us our y-intercept 0, 1. All right, now we're going to calculate f at positive 1. Again, replacing x with that value. And then 2 to the power of 1. Again, it's the identity element for exponents. 2 to the power of 1 is just 2. So on our graph, we'll have the point 1, 2. And our last x value here is 2. So we want to calculate f at 2. And that's going to give us 2 to the power of 2, or 2 squared. 2 times 2 is 4. And that completes our 5 coordinate pairs for this parent function for exponentials base 2. Let's label it that before we plot these points. This is the exponential parent function. What's a parent function? What makes a function a parent? I'll finish writing that. This is the exponential parent base 2. So a parent function is the most simple, the most basic of a family of functions. So you'll notice that that 2 to the power of x doesn't have a lot of parts, but it gives us a starting place, a basis for building more complicated descendant functions. Well, let's graph this one. So we have -2 half. And notice my scale here, each of those marks is 1/2. In fact, I made an error. It's not -2 half, it's -2 1/4. So I need to go in between. All right, that fixed it. -1 is at half. Better. 0 is at 1. Now we mentioned that that was our y-intercept. So notice as I plot the point, it becomes clear that that definitely is where the graph crosses the y-axis. We have 1, 2, and 2, 4. Now there's a lot of other points on this graph. What we have placed here is just a framework. So what I need to do is I need to fill in with the rest of the graph. Now my knowledge about exponential functions is that they don't ever cross the x-axis. So I'm very carefully trying to skate above the x-axis on the left side. And then very characteristic of exponential growth functions, they make a real sharp turn when they enter quadrant 1 and start to grow exponentially. That's where we get that term. Okay, so we've finished that first task. We've graphed the exponential parent function base 2. At this time, our task is to analyze for these list of characteristics. Now, as you're graphing, you're bound to notice some of these. In fact, we've already analyzed for the y-intercept. So I'm going to plot here the y-intercept at 0, 2. Again, that's where the graph crosses the y-axis. And I'm going to just mark off here on the graph that we calculated y-intercept. So as you're going through your work, if you can label these items for analysis on the graph itself, or if you want to list them below the graph, that's good too. You'll have room on your work to do so. All right, so I'm going to also notice this idea of the fact that this graph never crossed or touched the x-axis. So to make that kind of clear, I'm going to dash a red line there on the x-axis. And remember from your work in Algebra 1 and Algebra 2 that that is what we would call a horizontal asymptote. Now, I want to give not only that dashed line to show where it is geometrically, I also want to give the equation for that line. So we need to remember how to name a horizontal line. And really the question is, does it start x equals something or does it start y equals something? So on that line, I'm just going to pick out 2 or 3 of these points and I'm going to label their coordinates. So I see -6, 0 is there on that horizontal asymptote. I'll pick another one. I think 2, 0 is there. And it looks like 7, 0 is there. So there's a lot of other points, infinitely more points on that dashed red line. But what I'm trying to see with those three that I pulled out is what is the same for those 3 points. Is the x value the same or is the y value the same? So we can just investigate. -6, 2, and 7. Those are my x values. So I wouldn't start this equation for that red dashed line, x equals, because the x's are all different. The y values, however, are all 0. In fact, if I picked any point on that dashed red line, the y value would be 0. And so what I'm going to do is label that line y equals 0. So if you happen to forget how to write the equation for a horizontal line, in this case a horizontal asymptote, just pick some points off the line and see what's the same. Are the x's the same or are the y's the same? All right, so I'm going to cross off horizontal asymptote. We got to ask ourselves, is there a vertical asymptote for this graph? So a vertical asymptote would be an up-down dashed line that the graph never crosses, never touches. We might be tempted to think there's one here on this right side, but in fact, that's not really an asymptote. That's just the function getting very steep. It continues to the right as it goes up forever. So in fact, what we see is there's no vertical asymptote. And you'll start to see, we'll abbreviate that VA just to be efficient. Okay. Now, one of these other items, we've got domain, range, and zeros left. One of those is tied to the fact that there is a horizontal asymptote. Remember, a 0 is what we would call an x-intercept. We saw that on the x-axis, that's how we named that line. All the y values are 0. That's what we call zeros, zeros. It's where the graph crosses the x-intercept or the x-axis. Well, if my graph never touches or crosses the x-axis, can it have a 0 or an x-intercept? No. So again, part of what we're seeing is when we've answered parts of the analysis, it tells us information about other parts. In fact, it tells us perhaps there isn't something like a 0 on our graph. All right, well, that leaves us domain and range. So let's just remember about domain, what that is describing. Domain describes all of the x values in the function. So what we have to ask ourselves really is from left to right. That's the x direction. Where does this graph exist? Are there any gaps? Are there any holes? Or is the function real smooth and continuous and it goes across all the x values? Well, let's investigate for this exponential parent base 2. So over here on the left, we traditionally call that negative infinity. And what that's saying is over to the left, all those numbers become negative, more and more and more negative as you go to the left. On the right-hand side, we would call that positive infinity for the same reason, with the difference that the sign on the right is positive, and the numbers climb and get larger and larger and larger the more we go to the right. So as I write my domain, I need to ask myself, from the left to the right, are there any places in the graph where there are gaps or breaks? So as I look at this exponential base 2 parent function, it is perfectly smooth, perfectly continuous across what we see. And algebraically, there's nothing that would make any of these outputs, or I'm sorry, that would prevent us from using any particular x value. So what I'm going to write is domain is from negative infinity, which is less than x, which is less than positive infinity. There's other ways to write that. We could write it all real numbers. Those are equivalent statements. There's also a very efficient way that we learned in Algebra 2 to write that same description, negative infinity less than x less than infinity. Remember, with interval notation, we can drop the variable x and just put parentheses, negative infinity, comma, infinity, close parentheses. So there's 3 ways to write the same description. Well, we wrote the domain, and let's finalize our analysis by describing the range of the graph. So if we think domain was about the x values, range will be about the y values. So just like we did with the domain, I want to look at the graph to describe the range. Now, range is from the bottom of the graph to the top of the graph. And I do have negative infinity below and infinity above. And I just need to investigate where are the y values of this function. Now there's a clue here for us for the range. We've got a horizontal asymptote. And remember, an asymptote's an imaginary line that the graph does not cross, does not touch. So if I've got a horizontal asymptote, it means my y values start right above it and go up. Below it, the graph just doesn't live there. It's not present. So I'm not going to go from negative infinity, because down here in quadrants 3 and quadrants 4, the graph does not live there. Where the graph lives is above this horizontal asymptote. Now we saw that that y value was 0. So the way I'm going to describe my range is that it is from 0, strictly less than y, and again that y describes that's where the graph lives, all the way up to infinity. We could write that in interval notation as well. So again, the parentheses says the graph doesn't equal that number. Our graph would never have a y value equal to 0. We can see that algebraically because even when we had these negative x values, the output was always positive. The negative exponent just flips the base over. So this is from 0 to, I think we can safely say that that goes to infinity. And that completes our second task. So for each of these questions, you want to graph the function by creating a table of coordinate points, and then analyze for domain range zeros, y-intercept, horizontal, vertical asymptotes. Let's see one more example. So that was the exponential parent base 2. Let's take a look at a relative of the base 2 exponential. So this is f of x equals logarithm, that's how you say that, logarithm, base 2 of x. So we'll begin again by creating our table. And I'm going to put x and f of x. And again, I'm just going to place my negative 2 through positive 2. So negative 2, negative 1, 0, 1, and 2. Now we need to see, can I make this table by hand like I did the first table? So I'm going to start off, you always want to try it because there's value in just seeing how the numbers are generated. So we're going to go for f at negative 2. And we're going to just substitute negative 2 anywhere I see x. So this is logarithm base 2 of negative 2. Now, logarithm is really the inverse of the exponential. And that's why I said at the beginning, this is a relative of that first parent function we saw, 2 to the power of x. The way that we would evaluate output, so y values for a logarithmic equation, is by converting it to an exponential. That's how they're related. Now the way I do that is I start at this base 2, and that becomes the base to my exponential. Now I'm going to go in a clockwise circle across the equal sign. So it's 2 to the power, f at anything is really some y value. And that's what we're trying to find. So it's 2 to the power of some y value equals, because we're crossing back over the equal sign to what we would call the argument of the logarithm, equals negative 2. Now, I got to ask myself, can I raise a base to some exponent and have that output be negative? So can I raise 2 to a power and make it negative? Well, a negative number wouldn't do it. Remember back to our example previously, we had an asymptote at the x-axis. So none of the negative numbers push it down below the x-axis. So what we would have to say is that this value is undefined. There is no exponent that I could raise to the 2 to the power of that would make it -2. And I think as we go along, we're going to run into the same problem with f at -1. We'll try it. So f at -1 equals log base 2 of -1. Again, to see how to evaluate that, we'll begin with the base of the logarithm. So that becomes the base of the exponential. 2 to the power of y, f at -1 is a y value, equals, and then swing back to the far right side, -1, same problem. I'm trying to raise a positive base to some power and have it become negative. That never happens. So what we would say again is that's undefined. Well, let's see if we can do something with 0. In algebra 1, algebra 2, and pre-calculus, persistence is key. So we'll keep going, even though we kind of have a feeling like this is almost 3 strikes and we're out. So f at 0 equals log base 2 of 0. Now this is a different question. Notice that 0, that's not negative. So the idea is, can I raise 2 to some power of y and have it equal to 0? 2 to the power of y, does that have a value that could make that base 2 turn into 0? Well, again, we can think back to our base 2 parent function. The horizontal asymptote was right on 0. The graph never touched it. We didn't have any zeros, remember? So just like with the negative values, we cannot take the logarithm and get a 0 value. So 3 strikes. Are we out? No, we're not out. In math, you can have many, many strikes. So we'll keep going. We just are going to persevere through our table. So here we want to say f at 1. I really hope that we can do something, because you start to feel like you haven't made progress, but we've seen 3 things that are undefined. We'll see how that shows up on the graph. Well, this is f at 1. So now I'm going to say 2 to what power of y would equal 1? Is this possible? And eureka, we're in luck. Remember, what power can I raise anything to and have it equal 1? Excellent, 0. So the output here for the y is 0, and at last we do have a point that we can graph. This is the point 1, 0. Well, let's see if we can have that same type luck with our last evaluation, f at 2. So that's log base 2 of 2. And again, to find that output, we're going to convert to an exponential. So base 2 to the power of some y value equals 2. Back to the argument. 2 to the power of something equals 2. And again, we're in luck. Remember, we talked about the identity for exponents. If I put a 1 there for y, 2 to the power of 1 is 2. So that output is a winner and a keeper as well. So that's 1. And we've got another point here, 2, 1. So let's graph what we've got. Now I've got a lot of undefined values, which says for me that the quadrant 2 and quadrant 3 are not where our function lives. So quadrants 2 and 3, see how all those x values that are in between quadrants 2 and 3, those are all negative x values, including 0. Our function doesn't exist there. But I have a feeling that there is a vertical asymptote here on the y-axis, which is like a border or kind of a cutoff point for our function. So I think our function is here in quadrants 1 and 2. I'm sorry, 1 and 4. Make sure I count our quadrants correctly. Well, let's graph what we have in terms of points. So I just had the 2. We had 1, 0, So right there, and again, as we graph, we see some of the analysis. That's a 0. We'll catch that in a moment. 2, 1 is also on the graph. Now, that's a very, very, very basic framework. So one thing that you'll start to see, and we'll look at this with our last two examples, examples 3 and 4 in a moment, is that if you get a framework in place and you're still not quite sure what the graph looks like, you got to think to yourself, what other tools do I have at access? What do I have in my tool belt? And that is always going to include a graphing calculator. So you go through this analysis, you make the table, get some values, and get a framework in place. Now, I am fortunate. I've graphed this logarithm base 2 before, so I know what it looks like. But we'll go ahead and show the graphing calculator for the next two examples. We'll just sketch this graph though right now. So the logarithm base 2 function starts along the y-axis, and then as it passes into quadrant 1 from quadrant 4, it veers to the right really sharply. And that is our graph for our logarithm base 2. Let's write the name of that. That's logarithm. And one thing to note is that this is definitely a relative of the exponential base 2 parent function. And the relationship that we give to this is that they are inverses. So notice one thing, on the exponential base 2, we had a horizontal asymptote at the x-axis. Here on the logarithm base 2, we have a vertical asymptote at the y-axis. And one thing that we'll see, and really we'll see this more next unit, is that inverses switch their domain and their range. Okay, well, let's go through our second task. So we've finished that first task of graphing. At this point, we just need to analyze. So we've seen some things already. Let's identify the vertical asymptote. So that's here on the y-axis. And let's think, how would I name the y-axis? So again, I'm going to pick some points that are on that dashed vertical line. So 0, 6 is there. We'll pick a few. 0, 2, 0, negative 3. And just like we did for the horizontal asymptote, we just want to ask, what's the same? Are the x's all the same, or are the y's all the same? So as I look at the x's, they are all 0. So as I go to name this line, I really don't need to look at the y values. In fact, the y values are all different. 6, 2, negative 3, whatever. They could be anything. But even in the midst of that, the x values are all the same. So the way that I would name this vertical asymptote is x equals 0. So my VA, my vertical asymptote, is x equals 0. Again, on your work, if you just want to label on your graph, I don't have a lot of room around the graph, or you could do so right under the graph as well. Does this have a horizontal asymptote? Good. No, it doesn't. So there is no horizontal asymptote for this graph, which tells me I should be on the lookout for a 0. In fact, we saw a 0 already. So that's that point 1, 0. And remember, another name for a 0 is the x-intercept. And let's go ahead and label it. So I'll put both names for that feature of the graph, the 0 and the x-intercept. I'm going to erase quadrant 4 there. Let's label that. That's the point 1, 0. Let's consider for a moment whether or not we've got a y-intercept. We do have a vertical asymptote here on the graph. So think again what that would imply for our y-intercept. If I've got a vertical asymptote, does the graph cross the y-axis or touch it? Good, no, it doesn't. So what we would say is that this graph, although it has a 0, it has no y-intercept. The last thing to describe here is the domain and the range. So again, remember, domain is about x. We'll do that in green. And I'm going to put negative infinity and infinity here on the left and the right of the x-axis. But unlike the exponential function, this graph doesn't exist in quadrants 2 and 3. And so where I'm going to begin my domain is from the vertical asymptote 0. My domain is from 0, which is less than x, less than all the way to positive infinity. That graph does go sharply to the right over into quadrant 1. Again, we could record that in interval notation more efficiently as parentheses 0, comma, infinity. Our last description here is range. Range. So again, that's a y description. So I'm going to put negative infinity down there at the lower part of the graph, infinity at the upper part. And we've got to ask ourselves, are there any places where this graph couldn't have a y value? So definitely on the lower part, it starts at negative infinity. We can see that clearly how it has its root down, 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 down at the lower part of the graph. So negative infinity is less than y. And we've got to ask that upper part, it's going sharply to the right. Is it also increasing as it goes to the right? Yes, it is. So although the increase in the y is slower here than it is with the exponential function, it does still go to positive infinity. If we were to track it as x gets larger, it still rises. It never stops rising. And we could finalize that with our interval notation for negative infinity, comma, infinity. And again, we use those parentheses because that function, well, can you ever equal infinity or equal negative infinity? Those are moving values. Infinity is a constantly moving number. So we can't equal something that's always moving. And that's why we use the parentheses. The parentheses in interval notation mean the graph gets close to that value, but it never actually equals that value. Okay, so that's 2 of our examples. We'll pause here and allow you to go work on some of the graphs and analyses of your parent functions. And we'll come back in a moment for examples 3 and 4. Thank you for joining. See you in a moment.